Hello, this is Team 5 presenting the temperature controlled 3D printer enclosure. The team members include Juliana Nguyen, David Rubio, Jonathan Johnson, and myself, Anan Shahid. Here we have the table of contents. We have first, we'll go over the introduction, followed by the motivation, objectives, methodology, results, and finally, we'll end up with the discussion. For an overview, this team is going to design an enclosure that houses a 3D printer and regulates the internal temperature of the 3D printer. To start, the team has to start with conducting the research on the thermostat and the HVAC air systems. Then move on to modeling the actual system using the CAD softwares, and then move on to actually programming using the MATLAB Simulink. We use the state-specific controllers with relevant assumptions. And finally, we create a video report to communicate the whole process behind what went into the project. For the introduction, thermostats are being used as a regulating device, and sensors are installed to manage the temperature near a desired set point inside the enclosure, so that if the temperature increases or decreases outside the range, the temperature sensors can activate and send the signals to turn on the heat or turn off the heat to manage the temperatures. Also, the thermostats will have a set overshoot, which will allow the system to kind of stop running so we can save on electricity costs when it's not needed. Here you can see on the left side the heated enclosure that the team is working on. This design is able to maintain a constant temperature, and its enclosed area reduces the exterior influence. On the right side, however, you can see a non-enclosure open design, which provides an open exterior frame, and the printed parts are also exposed to the outside temperature, not to mention the debris while there's a product being printed. So our project basically prevents outside debris and also manages the internal temperature of the enclosure. The motivation behind this project is basically the current DIY enclosures are not reliable, the setup is difficult, and buying a printer with an enclosure is expensive. We focus on undergraduates who are working on projects and want to test their projects and build prototypes and are not having a budget to buy a really expensive enclosure printer. So we created an efficient, reliable, and cost-saving product that the professionals and hobbyists can use. The thermostat system can be inexpensively designed, leading to an affordable enclosure. Like I mentioned before, MATLAB Simulation provides a reliable program to simulate the dynamics of the system as well. I'll hand it over to Nguyen to take over the objectives of the project. Thank you.
Thank you, Answer. The objectives of the project are to model the thermal balance in an enclosure for a 3D printer. The 3D printer includes a heating system that receives input from the thermostat in an enclosure and stays between a temperature range. Environment for the 3D printer to work at a set temperatures depending on the material being printed. Develop second state variable based on temperature, volume, and heat flow. Next slide, please. On this slide, we have temperature specs for four popular materials: ABS, PLA, polycarbonate, and PETG, we try to achieve this temperature. Our target temperature range for the chamber is around 40 to 60 degrees. Next slide, please. On this slide, we have a CAD model of the actual 3D printer with the enclosure part is going to look like. I'm passing it on to Juliana.
Thank you, Nguyen. For the methodology, we made several assumptions, a few of them being that we're dealing with a steady state system, and we're assuming that no heat is lost from the system to its surroundings. The enclosure itself, we are designing one of which will be made out of plexiglass, and the length of it being about 0.72 meters, the width 0.65 meters, the height 0.55 meters, and it'll have a window, so you can see, and that would be a width of 0.3 meters and a height of 0.3 meters. The thermal conductivity of the walls are 136.8 joules per hour meter Celsius. And the specific heat of air, as we know, is 1,005 joules per kilogram Kelvin. So those are some of the parameters that we're dealing with. For our thermostat, it's going to be our relay block. It will control the fluctuation in temperature. So once it drops below a certain temperature, it'll turn on the heater. The heater will then model the constant airflow and calculate the airflow rate based on raw data. And the thermostat turns, like I said, the heater on or off depending on the temperature inside the enclosure. The enclosure will have to deal with the outside temperature of the environment and the inside temperature of the enclosure and the airflow rate within the enclosure. For some of our equations, we used the rate of heat gain, where the mass of the heater air is represented by the equation above, with the heat capacity and the temperature of air in the heater and the temperature in the chamber. We'll also use the rate of heat loss from the chamber to the environment and the change in chamber temperature as modeled by the equations in the slide. Here you'll see our Simulink block diagram modeling the thermal enclosure. And this was modified to fit our project application. And I'll pass it over to Jonathan for the results.
Thank you, Juliana. So here you can see the results of the graph of, we have a sinusoidal input, which means that the temperature will be varying outside. And you can see that the thermostat is able to keep a steady temperature with slight tiny variances in between. And you can see too the energy cost is going up at an almost constant rate. Next slide, please. Here we have the similar results with the step function. You can see that the temperature is able to stay steady as well. The step function, once it decreases in temperature, the temperature inside the enclosure stays constant. You can see that our energy cost as well is almost linear. It stays constant. Next slide. Now I'm going to pass it on to David Rubio for the discussion.
Thank you, Jonathan. And so just to quickly discuss back over it, with the step response, the system was able to compensate for the temperature decrease, and then it goes back to a steady state. With a sinusoidal response, the system can adjust to the temperature fluctuation over time. And with the impulse response, the system will adjust to the spike in temperature, and it comes back to a steady state. And so looking at our energy and cost analysis, our energy will cost about $1 more per hour, but it's going to save on the initial printing costs due to preventing waste of material and parts that would be unusable. The outside temperature will be varying sinusoidally, and our enclosure specs is that the enclosure can meet the lower end of the temperature range for PLA, PETG, and polycarbonate. It does not hit the recommended range for ABS, but it will still provide the benefit. And our concerns for this is that the fluctuating change in the outside temperature during the operation is a fairly low risk due to the most printers being located indoors in a controlled environment. Excellent. And so here are the technical references that we used. Thank you.